I've had a request on Twitter. You can see the tweet below for the top tips for F325 video to be reposted. So I've had a quick look at the slides from last year and I've changed some of them. So here's a brand new one for the exam for tomorrow, and very best of luck. So first one, always refer to chemicals given in the question. So a classic example of that is buffer solutions. If you're told what the buffer solution is made from, you can't get away with saying because it contains a weak acid and its conjugate base. You've got to specify what the weak acid is and what that conjugate base is. So for the Gibbs equation, put everything into kilojoules. So delta S is in joules per Kelvin per mole. So get them into kilojoules by dividing by 1000. And remember, the temperature is in Kelvin, so you have to add 273 onto the degrees C if it's given in Celsius. Calculating entropy change, it's products minus reactants. So I've got the SPA way of remembering it. S for entropy, products minus reactants. If you're calculating the enthalpy change of reaction using enthalpy change as a formation, it's products minus reactants. So for par is the silly word I use to remember that one. If a question asks for units, remember to put them in, and if there are no units, say there are no units. Born-Haber cycles, don't forget your state symbols. You can only make one change per arrow. Don't forget the electrons. And if there's a 2 in front in the cycle, remember to double. And obviously a down arrow in a cycle represents an exothermic process, and an up arrow represents an endothermic process. Factors affecting lattice enthalpy and hydration enthalpy is ionic charge and ionic radius, definitely not atomic radius. Standard electrode potential half equations, they're always written as reduction processes, so there's always involving a gain of electrons. The half equation with the most positive electrode potential moves in the forwards direction, gaining electrons more readily than the rest. Often asked what's the most powerful oxidizing agent, so that's the species which gains electrons the most readily. So it's the species on the left hand side in the half equation with the most positive standard electrode potential. If they ask you for the most powerful reducing agent, that's the species which is going to donate its electrons most readily. So it's the species on the right hand side in the half equation with the least positive standard electrode potential. So the reducing agent, remember, is on the right. They like to ask what are the processes taking place at each electrode. So the system with the most positive electrode potential is the positive electrode. That's the cathode, not the anode as you taught in electrolysis at GCSE. It's the other way around in these types of cells. So the positive electrode is the cathode. Reduction always takes place at the cathode. Red cat is my way to remember that. So if we look at the opposite of that now, so the system with the least positive electrode potential is the negative electrode, and that is the anode. So the oxidation takes place here, and I just remember it with the word oxana. Writing half equations, so typically you would balance for mass using H plus and water. However, if it does specify it's in alkaline conditions, you use hydroxide ions and water. So I normally do that first. I then look at the charge on each side of the arrow, get it the same using electrons, make sure both balance. A little bit on transition metals now. So scandium and zinc. Scandium only forms Sc3+, so its electronic configuration is just that of Ar, argon. Zinc only forms 2+, so it's argon's configuration 3d10. So they're not transition elements because they don't form an ion with a partially filled d subshell. and those 4s electrons, they go in first, but they come out first when you're making the positive ions of transition elements, and that's obviously compared to 3D. So 4s fills before 3D, but they're also lost before 3D. Chromium and copper, they're the weird ones because they have that 4s1 configuration. So you can see the configurations down there. pH of anything is minus log of the hydrogen ion concentration. The pH of buffers, so the H plus concentration is acid over salt, and then you would obviously minus log that. The pH of weak acids, the H plus concentration is the square root of Ka multiplied by the HA concentration, so square root of Ka is the way I remember it. Buffer solutions work best when the desired pH is the same as the pKa in the weak acid. It's okay, the buffer will work okay so long as the pH and the pKa only differ by plus or minus 1. pH curves now. The vertical section tells you the end of the titration. So sometimes they'll get you to do a titration calculation and you use that vertical line there to get the volume, in this case of the alkali used. When you're choosing the best indicator, its pH change or pH range must be in the vertical section of the titration curve. Kc is the equilibrium concentration of products over reactants, so it's a measure of how far the equilibrium is to the right or the left. Obviously, if Kc is greater than 1, you've got a higher concentration of products to reactants at equilibrium, and vice versa. Those square brackets, that little c in Kc stands for equilibrium concentrations, and they're obviously measured in moles per decimeter cubed. And if you're given the volume of the container in the information, you need to factor that in to calculate the concentration. So moles over volume for that. And the other thing to remember about Kc is that it's only affected by temperature. So if you're asked to explain a change in pressure, let's say, in terms of Kc, the first thing you should say is Kc is not affected by pressure, and then look at how the concentrations of the products and reactants need to shift to keep Kc the same. Rates, a constant half-life means a first order reaction with respect to a particular reactant. If you've got a reactant in a large excess, then a change in its concentration is not going to have any effect on the rate, so you'd class that as zero order. And just like the equilibrium constant, the rate constant K is only changed by the temperature. And as I said at the start, the very best of luck.